Welcome, everyone. Today, we're going to explore an interesting topic in machine learning. The focus will be on the FindS algorithm. On this first slide, you can see an illustration that visually explains how the algorithm progresses. Over the next few slides, we'll break down each step and see how the FindS algorithm helps us in machine learning. Let's get started. Let's take a closer look at the FindS algorithm. This is a pretty straightforward concept learning method that helps us find the most specific hypothesis that still fits all the positive training examples we have. Essentially, it starts with the most specific hypothesis possible and then generalizes only when necessary to accommodate positive examples. What's important here is that it follows a specific to general search approach. That means it begins with the most restrictive hypothesis and gradually broadens it as needed, rather than starting broad and narrowing down. Now, to make this clearer, I'll walk you through a step-by-step explanation using the classic enjoy sport example. This example is a great way to see how the algorithm works in practice, showing how it updates its hypothesis to fit the data. The main aim here is to find a hypothesis, which we'll call H. This hypothesis is essentially a rule or a model that can predict whether a person will enjoy playing a sport or not. The prediction is based on various weather attributes. So, we're trying to answer the question, given certain weather conditions, can we predict if someone will say yes or no to enjoying the sport? To help us understand this better, we have a training data set. This data set includes several examples, each with specific weather conditions and whether or not the person enjoyed the sport. For instance, the first example shows a sunny sky, warm air temperature, normal humidity, strong wind, warm water, and the forecast being the same, which resulted in a yes for enjoying the sport. Similarly, the second example also has sunny weather and warm temperature, but humidity is high, and again, the person enjoyed the sport. On the other hand, the third example features rainy weather, cold temperature, high humidity, and a forecast that indicates change, which resulted in a no. By analyzing these examples, we can start to see patterns and factors that influence whether someone will enjoy the sport or not. The ultimate goal here is to develop a hypothesis that captures these patterns, allowing us to make accurate predictions based on weather attributes in future situations. This process is fundamental in machine learning, where we aim to find models that generalize well to new, unseen data. Let's start with step 1, initialization. Here, we initialize the hypothesis, which we call H, to the most specific hypothesis possible within our hypothesis space. Denoted by H, this most specific hypothesis is represented by the symbol letter 3D5, or phi, and it basically means that no instance in our data satisfies this hypothesis initially. So, we set H0 equal to a vector where all elements are letter 3D5, like this. H0 equals less than, then phi greater than. This setup is important because it provides a starting point for our learning process, an initial hypothesis that we can then refine as we see more data. Think of it as setting a baseline that is as restrictive as possible, and from there, we expand or adjust our hypothesis to better fit the actual data. This step is fundamental in algorithms like version space learning, where we iteratively narrow down the hypothesis space. So, by beginning with this most specific hypothesis, we ensure that we're starting from a point that doesn't falsely include any incorrect hypotheses, allowing us to make more accurate updates as we proceed. Now, let's move on to step 2, iterate through training examples. The key idea here is that our algorithm only considers positive examples when updating the hypothesis. So, when we process a positive example like x1, we're going to make some updates. For instance, x1 is sunny, warm, normal, strong, warm, same, and the target is yes. Since x1 is a positive example, we need to update our initial hypothesis, which we call h0. Because h0 is completely letter 3D5, meaning it's as general as possible, we now generalize each attribute to match x1. This results in our new hypothesis, h1, which is exactly sunny, warm, normal, strong, warm, same. This process of updating based on positive examples helps us refine our hypothesis to better fit the data. Let's take a look at the process for updating our hypothesis with this positive example. We start with the example data. Sunny, warm, high, strong, warm, same, and the target is yes. Since this is a positive example, we compare it to our current hypothesis, H1, and see where they differ. For each attribute, if they match, we keep that value in our new hypothesis. If they differ, we generalize that attribute to a question mark, indicating any value is acceptable. In this case, sky is sunny in both, so we keep sunny. Air temp is warm in both, so we keep warm. Humidity differs. We have normal here, but the example shows high, so we generalize to. Wind matches strong, so we keep strong. Water matches warm, so we keep warm. Forecast matches same, so we keep same. This results in our new hypothesis: sunny, warm, strong, warm, same. This process illustrates how we refine our hypothesis to better fit the positive examples, progressively narrowing down the conditions that lead to a positive outcome. Now let's look at the process when we encounter these negative examples. We have 3 instances with features like rainy, cold, high, strong, warm, and change, and the target is no. These are called negative examples. The important thing to note here is that the FindS algorithm ignores these negative examples. It does not change its hypothesis when it sees them. Instead, it only updates based on positive examples. As a result, our hypothesis remains the same after processing these negatives, which is why H3 stays equal to H2, with the features sunny, warm, strong, warm, same. This highlights a key point. The FindS algorithm is designed to only generalize from positive data, which makes it simple but also somewhat limited because it doesn't explicitly account for negative information. Understanding this helps us see how the algorithm's assumptions influence its behavior, especially in real-world scenarios where negative examples are just as important as positive ones for shaping accurate hypotheses. Now let's walk through process X4, where we're working with the positive examples sunny, warm, high, strong, cool, change, which is labeled as target. Yes. Since this is a positive example, we compare it to our previous hypothesis, H3, and identify where they differ so we can generalize accordingly. Starting with the sky feature, both the example and H3 have sunny, so we keep sunny. For air temp, both are warm, so again, we keep warm. When looking at humidity, the example has high, but H3 had a question mark, indicating it was already more general there, so we keep the question mark. Moving on to wind, both are strong, so we keep strong. For water, the example has warm, but H3 had cool, so this is a mismatch. To accommodate both, we generalize water to a question mark. Lastly, for the forecast, the example has change, but H3 had a question mark, so we generalize the forecast to a question mark as well. This results in our new hypothesis, H4, which is sunny, warm, strong. The key takeaway here is how we iteratively generalize our hypothesis to cover positive examples while aiming to avoid overgeneralization. This process helps us refine our model step by step, making it more accurate and robust as we encounter new data. Now let's look at step 3, output. After processing all of our training examples, the final hypothesis, which we call H4, is the most specific hypothesis that still fits all the positive examples. Essentially, it's the most detailed rule that doesn't contradict any of the examples we've seen. The final hypothesis is represented as H equals, and it looks like this: sunny, warm, strong. What does that mean? Well, it predicts that a person will enjoy the sport if the sky is sunny, the air temperature is warm, and the wind is strong. The question marks indicate that for humidity, water temperature, and the forecast, the hypothesis doesn't specify any particular condition. It doesn't matter what those are, the prediction still holds. This is a great example of how the model zeroes in on the most critical features, those that are consistent across positive examples, and ignores the rest. It's a way of capturing the core conditions for a positive outcome, which in this case is enjoying the sport. So overall, this final hypothesis helps us understand exactly what conditions are most influential in making a correct prediction, regardless of other variables. It's a powerful concept because it shows us how machine learning models can focus on what truly matters in the data. Thank you for watching. Like, share, subscribe to EC Learning 360 YouTube channel.